In this lesson, you are going to understand the concept of recommender systems. By the end of this lesson, you will be able to build a recommender model using Python, describe the mechanism of association rule mining, demonstrate a priori algorithm. So let's go ahead and understand recommender systems in detail. So what is a recommender system and how is it useful? Many e-commerce and retail companies implement recommender systems on their websites to leverage the power of data and boost their sales. In other words, the goal of a recommender system is to predict users' interests and recommend products that the users may be interested in. Data required for recommender systems stems from explicit ratings that users provide after watching a movie or listening to a song, from implicit search engine queries and purchase histories, or from other knowledge about the users, items themselves. Recommender systems are one of the most successful and widespread applications of machine learning technologies in business. It is an information filtering technique that provides users with recommendations that they might be interested in. As you can see in the given image, interests of users A, B, C, D are given. Your recommendation system has to find out whether user E will be interested in music or not. Let's look at how recommendation systems are useful in day-to-day life. Recommendation systems act as a solution for many of your day-to-day choices, such as which website will you find interesting, which degree or university is best for your future, which is the best investment for supporting the education of your children, which digital camera should you buy, which book should you buy for your next vacation, which is the best holiday for you and your family. Before we explore this topic, let's think of how a recommender system recommends items to users. It recommends items that are more popular among all the users. It divides users into multiple segments based on their preferences, that is, user features, and recommends items to them based on the segment they belong to. In the given example, you can see that when you go to buy a book on Amazon, it recommends books that are frequently bought together, and also gives you insights under customers who bought theirs also bought this. Let's understand the purposes of a recommender system. Prediction perspective. It predicts to what degree a user likes an item. It is the most popular evaluation scenario in research. Interaction perspective. It educates users about the product domain. Conversion perspective. It looks for commercial situations, such as increase in hits and click-through, and also checks lookers' and bookers' rate. Retrieval perspective. It reduces user search cost and effort by providing correct proposals or recommendations. Recommendation perspective. It identifies items from long tail where users don't know about their existence. Paradigms of recommender systems. Recommender systems reduce information overload by estimating relevance. As shown in the given image, a recommender system matches the relevance of the recommendation component with the recommendation list, and based on the relevance, it decides the recommendation. What are personalized recommendations? The most relevant item is recommended based on the user profile and contextual parameters. Every day, massive amounts of information are generated, and the existence of a large amount of information makes it difficult to find the required information. Personalized recommendation is the process of alleviating the problem. Now, let's understand how a recommendation system finds what's popular among your peers. Collaborative filtering recommendation algorithm uses the rating data to calculate the similarity between items. It does not consider the semantic relationship between different items. Let's understand what content-based recommendation is. It is used to display products similar to the products you have liked before. A content-based recommender works with data provided by the user, either explicitly, through rating, or implicitly by clicking on a link. Based on the data provided by the user, it generates a user profile. Suggestions are given to the user based on this. The recommendation engine becomes more and more accurate as the user provides more inputs or takes action on the recommendations. Knowledge-based recommender systems use knowledge about users and products to make recommendations about which product meets the user's requirements. A knowledge-based recommender system does not have a ramp-up problem as it does not create recommendations based on user ratings. Since knowledge-based recommendation systems' judgment is independent of individual tastes, it does not have to gather information about a particular user. These characteristics make knowledge-based recommenders not only valuable systems on their own, but also highly complementary to other types of recommender systems. Let's now understand how your recommender system can make combinations of various inputs and/or composition of different mechanisms. Hybrid recommender system is a system that combines content-based filtering and collaborative filtering and takes advantage of both the representation of the content as well as the similarities among users. It is also possible to use the recommendations of the two filtering techniques independently. Collaborative filtering Part A. Collaborative filtering systems make recommendations based on historic preference of the user, such as items clicked, watched, purchased, liked, rated, etc. User item matrix can be used to present these preferences. It uses filters either based on item-based nearest neighbor or user-based nearest neighbor. Let's understand user-based collaborative filtering. Well, user-based collaborative filtering recommends items by finding users similar to the active user, as in the given example. Based on other users, you need to determine whether Alice will take the buy 5, which is not seen or rated by her. Let's understand how you can measure user similarity using Pearson correlation. Degree of linearity can be determined using Pearson correlation. In other words, it determines whether there is a linear component of association between two continuous variables. As such, Pearson's correlation has no assumptions about linearity. However, when you already know the relationship between your two variables is not linear, you would normally not want to pursue a Pearson's correlation to determine the strength and direction of a linear relationship. Let's understand the given formula. In the given formula, A and B are the two users, and you are asked to find the similarity between them. The given formula will give you the result between -1 and 1, where 1 means highly similar and -1 means not at all similar. In the given formula, A and B are users. RAP is the rating of user A for item P. P is the set of items that are rated by both A and B. Now you have the similarity between different users for a specific item. Use these similarity values in making predictions. So a common prediction function is given on the screen. Here, sim AB is the similarity value obtained for users A and B. RBP is the rating of user B for item P. Collaborative filtering Part B. Now let's understand how item-based nearest neighbor works. Item-based approach is preferable to user-based approach. So what is the reason behind this preference? Because of the dynamic nature of users, user-based approach is often harder to scale as the items usually don't change much. Item-based approach often can be computed offline and served without constant retraining. KNN is the perfect go-to model to implement an item-based collaborative filtering. It is also a very good baseline for recommender system development. Look at the given example. In item-based collaborative filtering, you need to look for items that are like item 5 and then take Alice's ratings for these items to predict the rating for item 5. The choice of the K nearest neighbors for the neighborhood formation results in a trade-off. When you use a very small K, only a few candidate items can be recommended because there are not a lot of neighbors to support the predictions. While the particularities of users' preferences can be blunted due to the large neighborhood size, so a very large K impacts precision. The optimum K also depends on data characteristics such as sparsity. So K is set to be in the range of values from 10 to 100. The similarity is measured based on two algorithms, cosine and adjusted cosine. Cosine similarly has better impact in item-to-item filtering. Here, ratings are seen as a vector in n-dimensional space, so the angle between the vectors is used to calculate the cosine similarity, whereas adjusted cosine similarity takes average user ratings into account and transform the original ratings. Association rule mining. At a basic level, association rule mining involves the use of machine learning models to analyze data for patterns or co-occurrence in a database. It follows association rules, which is to identify frequent if-then associations. Given a database of transactions, each transaction is considered as a list of items. It finds all the rules that correlate the presence of one set of items with that of another set of items. It identifies the frequent patterns. It is most commonly used for market basket analysis. Association rules are created by searching data for frequent if-then patterns, using the criteria support, identifying the most important relationships. Support is an indication of how frequently the items appear in the data. It provides a fraction of transactions containing the item X and Y. Support is calculated as the number of times item X occurred divided by the number of transactions. Confidence indicates the number of times the if-then statements are found true. It indicates how often the item X and Y occur together, given the number of times X occurs. It is calculated as the number of times items X and Y occurred divided by the total occurrence of X. A third metric called lift can be used to compare actual confidence with the expected confidence. It indicates the strength of a rule over the random co-occurrence of X and Y. It is calculated as the number of times in X and Y occurred divided by total occurrence of X multiplied by total occurrence of Y. Association rule mining, market basket analysis. Let's understand the association rule using the given example. Market basket analysis is a modeling technique based upon the theory that if you buy a certain group of items, you are more or less likely to buy another group of items. And item set is the set of items that a customer buys, and market basket analysis is used to find the relationships between purchases. Here in the given example, A, B, C, D, and E are items in a store. P is the set of all transactions that are P1, P2, P3, P4, P5. So you can see that each transaction is a set of items. Consider you made some association rules using the given transaction database. Support is a measure of how much the historical data supports rules defined and confidence mean. Confidence mean is the measure of how confident we are that the defined rule holds true. Support can be calculated as the fraction of rows containing both A and C or joint probability of B and C. Among the rows containing A, confidence is the fraction of rows containing D or conditional probability of B given C. This is the ratio of confidence to support. If the lift is less than 1, then A and D are negatively correlated, else positively correlated. If it is equal to 1, it is not correlated. So when you are calculating support, confidence, and lift, values will result in the given matrix. Association rule generation, a priori algorithm. Candidate item sets with the a priori algorithm are created using only the large item sets of the previous pass. The large item set of the previous pass is joined with itself to generate all item sets with a size that's larger by 1. Each generated item set with a subset that is not large is then deleted. The remaining item sets are the candidates. It uses frequent item set to generate association rules. Frequent item set is a set of items whose support value is greater than the threshold value. With this approach, the algorithm reduces the number of candidates being considered by only exploring the item sets whose support count is greater than the minimum support count. A priori algorithm example part A. The number of item sets that have to be examined can be pruned using the a priori principle. The list of popular item sets can also be obtained. We have the given data of a store. Scan the transaction database to get the support S each one item set. Compare S with min sup and get support for one item sets. Let's assume the support value is. Create the item of the size of 1. Calculate their support values. As you can see here, item 4 has a support value of 1, which is less than the main support value, so we are going to discard 4 in the upcoming iterations. We have the final table F1. Start with item sets containing just a single item. Determine the support for the item sets. Remove the item sets that do not meet your minimum support threshold, and keep the item sets that meet it. Use join to generate a set of candidate K item sets. Use a priori property to protect the unfrequented K item sets from this set. Next, create item sets of size 2 and calculate their support values. All the combinations of items set in F1 are used in this iteration. Item sets that have support less than 2 are eliminated again, in this case 1, 2. The length of an item set is extended. All the combinations of item sets in F12 are used in new candidate key C3. Now let's understand what is pruning and how it makes a priori one of the best algorithms for finding frequent item sets. Using pruning, we are going to divide the item sets in C3 into subsets and eliminate the subsets that have a support value less than 2. A priori algorithm example part B. Scan the transaction database to get the support S of each candidate K item set in the given set. Compare S with min sup and get a set of frequent K item sets. Using sets of F3, create C4. Since the support of this item set is less than 2, we will stop here and the final item set we will have is F3. With F3, we get the following item sets. For 1 equals set 1, 3, 5, subsets are 1, 3, 1, 5, 3, 5, 1, 3, 5. For 1 equals set 2, 3, 5, subsets are 2, 3, 2, 5, 3, 5, 2, 3, 5. We will create rules and apply them on item set F3. Now let's assume that the minimum confidence value is 60%. For every subset S of I, you output the rule. S is greater than IS means S recommends IS. If support I over support S is greater than or equal to min conf value. A priori algorithm rule selection. Based on the steps performed, a few rules have been selected and a few are rejected, so all the rules that are selected have a confidence value greater than 60%. For set 1, 3, 5, look at the rules. Rule 1. Set of 1, 3 greater than set of 1, 3, 5 minus set of 1, 3 means 1 and 3 greater than 5. Confidence equals support 1, 3, 5 over support 1, 3 equals 2 over 3 equals 66.66% greater than 60%. Hence, Rule 1 is selected. Rule 2, set 1, 5 greater than set 1, 3, 5 minus set 1, 5 means 1 and 5 greater than 3. Confidence equals support 1, 3, 5 over support 1, 5 equals 2 over 2 equals 100% greater than 60%. Rule 2 is selected. Rule 3, 3, 5 greater than set of 1, 3, 5 minus set of 3, 5 means 3 and 5 greater than 1. Confidence equals support 1, 3, 5 over support 3, 5 equals 2/3 equals 66.66% greater than 60%. Rule 3 is selected. Explain specifically why each and every rule is selected and rejected. Rule 4. Set of 1 greater than set of 1, 3, 5 minus set of 1 means 1 greater than 3 and 5. confidence equals support 135 over support 1 equals 2/3 equals 66.66% greater than 60%. Rule 4 is selected. Rule 5. Set of 3 greater than set of 135 minus set of 3 means 3 greater than 1 and 5. Confidence equals support 135 over support 3 equals 2/4 equals 50% less than 60%. Rule 5 is rejected. Rule 6, set of 5 greater than set of 135 minus set of 5 means 5 greater than 1 and 3. Confidence equals support 135 over support 5 equals 2/4 equals 50% less than 60%. Rule 6 is rejected. This is how you create rules in Apriori algorithm, and the same steps can be implemented for the item set 2, 3, and 5. Demo User Movie Recommendation Model. Problem scenario. Consider the ratings dataset below containing the data on user ID, movie ID, rating, and timestamp. Each line of this file represents one rating of one movie by one user and has the following format: user ID, movie ID, rating, timestamp. Ratings are made on a 5-star scale with half-star increments. User ID represents the ID of the user, movie ID represents the ID of the movie, and timestamp represents the seconds from midnight Coordinated Universal Time, or UTC, of January 1, 1970. Here you are supposed to predict a user movie recommendation model. Let's import the required libraries and the dataset. Also add column names against the dataset. Let's now print the resultant data frame. Since we are developing a user movie recommendation model, we must be aware of the number of users and the number of movies, so let us write the code for the same. Now we will split the data into training and testing sets, importing the train test split function from the sklearn.model selection module. First, create a zero matrix with dimensions as n_users and n_movies. Now that we have created train and test sets, we will populate the train and test metrics with ratings such that the user ID index minus movie ID index equals the given rating. We can now see that we have some movie ratings in the training set. We will do the same for the testing set. Now import the pairwise distances import from sklearn.metrics to create cosine similarity matrices for users and movies. Cosine similarity is a measure of similarity between two non-zero vectors of an inner product space that measures the cosine of the angle between them. The cosine is 0 degrees, is 1, and it is less than 1 for any angle in the interval 0 pi radians. Now we will go ahead with the predictions based on the fact that user-movie collaborative filtering's difference from mean rating is a better indicator than absolute rating. Calculate user prediction such that user prediction is the sum of the mean user rating and the dot product of user similarity and ratings difference divided by the absolute value of the user similarity. The matrix we received as output describes how those unrated movies will be rated by users based on their prior rating styles. Now that we have approximately generated ratings for all movies, let's quickly recap the steps we have covered. Import libraries and the data set. Identify total number of users and movies. Split the data into training and testing sets. Populate the train test matrices with the random ratings. Create cosine similarity matrices for users and movies. Perform predictions. This brings us to the end of Recommender Systems. You are now able to build a recommender model using Python, describe the mechanism of association rule mining, demonstrate a priori algorithm.
Hi there, if you like this video, subscribe to the Simplilearn YouTube channel and click here to watch similar videos. To nerd up and get certified, click here.